Okay, students, Bismillahirrahmanirrahim to today's lecture. Today we are going to do one small derivation and then we are going to do some practice problems. ठीक है, तो let me just open the book for you. Okay, जो एक last time derivation रह गई थी, we are going to complete that. Uh, okay, I'm going to share the book with you. I've opened the textbook for you. The book is here. Okay, so the one last derivation that we need to do is related to the power converted, the power output of the synchronous generator. We have done all this stuff. Okay, one relaxation that we can do to drive the equation for P converted is in equation 420 is that we again look at the phasor diagram for the generator. This is the phasor diagram for the generator, and we have the torque angle sigma over there, which was the angle between V phi and the armature induced voltage, as can be also seen in this diagram here. The diagram in which we were showing the relationship between the rotor and stator magnetic fields. So in this diagram, we see that this is the same torque angle sigma, which is between the V phi, which is the terminal voltage of the generator going to the load, and the primary armature induced EMF, which is EA. And from EA, we subtract the effects of the armature reaction because it is opposing it. And we subtract the effect of the armature losses, which are in the resistance and inductance of the armature. And the resulting terminal voltage going to the load is denoted as V phi. So the angle between V phi and the angle between the primary armature induced voltage is torque angle. It is called sigma. So this angle sigma is the same over here, and it is drawn between the same two phasors, which is EA and V phi. So we can see that this torque angle sigma is again between the vectors of EA, which is the primary armature induced voltage, and the V phi, which is the load voltage per phase. And this diagram is also drawn for per phase of the synchronous generator. It is never drawn for the line values. So in this diagram, we take a very simple relaxation, and that simple relaxation is that this one is showing a relationship for a lagging power factor load. So that's why you can see that EA is dipped below the V phi. V phi, the voltage going to the load is taken as the standard as the zero angle vector. So this diagram should actually have been like this. You should have had V phase and then IARA vector, just like in the case of the transformer for lagging loads. And then you should have this IA JXX vector, and then this resultant would have been equal to the armature induced voltage EA. Okay, so what we do in this diagram is that we ignore the effect of IARA. Okay, we take the assumption since IA is much less than the synchronous reactance of the generator. So this diagram, in this diagram, I've exaggerated IARA. This IARA vector would be very small compared to IAJXS vector. So we are trying to ignore this one because it is very small. So we are going to ignore the vector IA array altogether, and if we ignore this vector, the resulting diagram will just have three sides. Okay, Anjala, there's a question from Anjala. I saw a raised hand signal from Anjala Sumro. Okay, probably maybe by mistake. Okay, so instead of this four-sided polygon in this phasor diagram, then you are just going to result in a triangle, because you are going to ignore this IA RA vector because it is very, very small compared to IA JXS. Okay, so the resulting triangle would look like this, three sides, okay, when we ignore the IA RA vector. And in this triangle, we can have a relaxation, that this vertical side that I call V over here, this is equal to, if I take the projection of this vector on this vector, so it will be equal to, if I take the projection, what component of this vector is in this direction, so it will be equal to J XS IA cos phi, IA J XS and cos theta. Okay, but this V is also equal to, if I take the projection of this vector, just like I took the projection of this vector in the vertical direction, I can take the projection of this vector in the vertical direction, and the angle of this vector is sigma with the horizontal. Okay, so it will become EA sine phi. Okay, so this V is also equal to this, and this V is also equal to this, so we can equate the two quantities. And if I make uh, if I make the two quantities equal, EA sine phi and EA J XS, okay, we can remove the J thing because J is just indicating its phase. Okay, so we can just get rid of this J. And if I equate the two sides and I make uh, IA the subject of this equation, I make the IA the subject of this equation and put IA over here. So my P converted will be equal to P out. So why P converted would be equal to P out? Because now what I have assumed is that this copper losses are equal to 0. Because what I said was that IA RA is negligible. It goes to 0. That means IA is obviously present in the machine. It is the load current. So what I'm saying is, if RA is considered as 0, so if RA, armature resistance, is considered as 0, then the stator copper losses, because again, remembering this side is rotor side, this side is a stator side, all the electrical losses are considered here, all the mechanical losses are considered here. So if I neglect the stator losses, that means I can say that my P converted is equal to P out. Okay, so I take this relaxation that under these circumstances, P converted is P out because stator copper losses are very low. And if I make IA the subject uh, in this equation, IA cos phi, and back put it over here. So my expression for P out or P converted, because now the two quantities are same, so P out is equal to P converted, and it would become this. So it is 3V phi, which is as it is coming, and instead of IA cos phi, I substitute IA cos theta. I substitute IA cos theta with this expression. And how I got this expression? From here. Okay, so I make IA cos phi the subject here, and since the two quantities are equal, I can equate it to IA cos phi would be equal to EA sine sigma over XS. So that's all what I have put. EA XS, EA XS sine sigma over X, E uh, EA sine phi over XS. Sorry, XS is coming in the denominator, so I just put these gadgets over here, like here, and the resulting expression for P converted would be this. So if someone asks you to find P converted and you can relate the mechanical quantity, so the main key thing to notice, P converted is a mechanical quantity, but P out is a electrical quantity because it is a generator, and we are saying that since the stator electrical losses are 0, so the converted mechanical power, all of it is converted into the electrical output power, and the the beauty of this equation is it is trying to make you relate the mechanical parameters in terms of the electrical parameters. So you can see over on all of the parameters on the right hand side of this equation are electrical parameters. V phase is the terminal voltage of the generator. E is the armature induced voltage, primary armature induced voltage of the generator. This torque angle is also coming from the interaction of the magnetic fields. Xs is the synchronous reactance of the synchronous generator. So all of these electrical quantities are making you relate to the mechanical quantity, which is P converted. And obviously the maximum value can be attained when the torque angle is equal to 90. So the maximum power would be this. And you can also relate this to the you can also relate this that P converted is equal to tau induced over the synchronous into the synchronous speed omega m. So you can make tau induced as the subject of this equation and divide the P converted, which is also equal to P out under these circumstances, by omega m, and you can get the expression for tau induced. So equipped with this, you are now able to solve most of the problems. Are you okay up till here? Okay, so the main key thing that we did here was to relate the mechanical parameters of the generator in terms of the electrical parameter. We took an assumption that RA is negligible compared to the synchronous reactance of the generator, and using this relaxation, we have derived the expression. We have derived the expression for P out, which is also equal to P converted. P converted is the mechanical output of the generator. P out is the electrical output of the generator, but we relate the two as when we assume RA to be equal to 0, then we are ignoring the stator copper losses. Is everyone okay up till here? We will try to do some end of chapter numericals. Okay, is everyone okay up till here? Okay, please reply on the chat window. We are going to some end of chapter problems in which we are going to see 2-3 interesting scenarios that will help you. Okay, everyone is clear with it. So without wasting any more time, let's go to the end of chapter problem. Okay, so we are now doing because after this in the next class inshallah we try to move to the synchronous motors, and after that I'll give you an assignment and a quiz from the topic of synchronous generators and synchronous motors. Okay, so where are the end of chapter problems? Okay, summary, end of chapter problem. Okay, so now we are going to do problem number 4.2, 4.3, and there's another problem that we are going to do. Okay, 4.2 and 4.3 are related to this open circuit characteristics of the generator. Again, reminding you that in the question, every time the data you will get will be always in the form of line data. And whenever you are writing the equation to find the parameters, equations are always written in per phase format, and that phasor diagram is also drawn in the per phase format. Always remember that, and you all also know the relationship in Y and delta. So in this question, the generator is Y connected, and in the Y connected, you know that line current is equal to phase current, and line voltage is equal to under root 3 times the phase voltage. So everything will rotate around this concept. Since it is a Y connected synchronous generator, it's a 13.8 kilovolt, 50 MVA, that means 50 megavolt amperes, rating 0.9 PF lagging, 60 Hertz, 4 pole Y connected, and it has a synchronous reactance of 2.5 ohm and armature resistance of 0.2. Now this impedance data is always per phase. All the other voltage current data is always in the line form, but this impedance is never in the line form. This impedance is in the phase, per phase. Okay, because all of the 3 sets of coils of the stator are identical, so this is always per phase. Okay, and at 60 hertz, if friction and wind loss is 1 megawatt, its core loss is 1.5 megawatt. Because it is a very huge rating generator, so its core loss and friction loss is also very high. Field current has DC voltage 120 volts. Maximum IF is 10 ampere, as can be seen from this diagram. Diagram, this diagram. Okay, so if you look at this diagram, the maximum IF is going up to 10 amperes. This open circuit voltage is the value of EA line voltage at no load. Okay, so that is why it is called open circuit, because the load is not attached. Okay, and this current is DC. It is obvious, and you know that this current is this voltage is alternating AC. Okay, and the value is written in kilovolts here, and this is without any kiloamperes. Okay, so it says that it is 0 to 10 OCC is shown in this. So what will be the per phase equivalent circuit for this? So let's open the whiteboard. Okay, so in the DC side, the DC side will be for the field circuit, and the AC side will be for the armature circuit, and the field is located in the rotor. So you can draw the rotor side like this. There is some R adjustable. This is field resistance, so RF, and probably this inductor for the field circuit, and this is a DC circuit, and it is says that it is supplied with 120 volts. Okay, and now we draw the stator side. Okay, so now we draw the stator side. In the stator side, we have EA, and we know that EA is like a battery, it is supplying the whole thing, and there are then some drops. The drops are in the form of armature resistance and synchronous armature inductance, and the armature reaction is also embedded inside it, which is opposing it. So this also acts like a losses, and this is the terminal voltage that is given to the load. So it may be open circuit if the load is not attached, and if the load is attached, even this side will be closed. Okay, so now we have this, and we draw a small sine wave here to show this side is AC. So we know this is stator, we know this side is rotor, and we also know that this side is field and this side is armature, just for your revision. Okay, armature is located on the stator. Stator has AC parameters and rotor has DC parameters. Okay, you supply, we give DC to it, and we extract AC from it, since this is a generator. Okay, so just for your little revision, I have written those remarks. You don't need to write it every time. And now it says question part A. Let's look at the question and try to answer it. So we go back to the book. Book is here. The book says in part A, how much field current is required to make the terminal voltage or line voltage VL equal to 13.8 kilovolts. So this is the terminal voltage where the load will be attached. Okay, and the line voltage equal to 13.8 kilovolts when the generator is running at no load. So now the key point here is no load. So what happens at no load? It is saying that it is line voltage is equal to 13.8 kilovolts. Let's go to the diagram. Okay, so it is saying line voltage is equal to, that means that the terminal voltage, and we are drawing it for per phase. So we are saying that it should be per phase per phase terminal voltage V5 should be equal to divided by under root 3 Y, because the generator is Y connected. Okay. Okay, because the generator is Y connected, it says above over here, and we know that in the Y connection, the line voltage is under root 3 times the phase voltage, and we are drawing the diagram for the phase voltage, so we have to convert the line voltage into phase voltage, and the generator is running at no load. Okay, so what happens is, this is the phase voltage, per phase voltage, and this side is EA. And when there is no load, that means this circuit is open, that means the same voltage per phase will appear over here. Okay, same voltage per phase will appear over here. So EA per phase voltage would be equal to 13.8 kilovolt divided by under root 3. How much is this? If you calculate this, please tell me the answer. It would be 7.967 kilovolt. Okay, and this is the magnitude. I am not giving the angle, so this is just the magnitude of this voltage. Okay, now what it says in the question. Okay, we have drawn this diagram and stuff, and we are happy. But now let's look at the question. The question, it says, how much field current is required to make the terminal voltage V phase. So from this first relationship, we drew the relationship between EA and VL. Okay, so if the generator is running at no load, we drew the relationship that EA becomes equal to V5. Okay, because there is no current in the generator, so there are no losses in the generator, and all the voltage from EA will appear on V5. So per phase EA is 7.96 kilovolt and V5 is also 7.96 kilovolt. And for the field current, we need to refer to this. So that means we need to refer to this. But in this diagram, you see that EA is mentioned as line voltage. It is not mentioned as phase voltage. So that means we will again have to convert EA back to line voltage. So we are going to take that value 7.96 kilovolt, which is per phase EA, and again multiply it by under root 3 because it is Y connected. So we are going to go back to the value of 13.8 kilovolts. So because the data is always in line, so you take the value 13.8 kilovolt, and corresponding to this, your IF is about 3.5 ampere. So the answer for the first part is 3.5 amperes. Okay, because why we went back from the phase to the line value, because in the question I have told you all the voltages and currents are given in line voltage. So that 7.96 kilovolt was EA, but phase, per phase. And again, to go back to line voltage, you go back to 13.8 kilovolt, because the data in the question is always referring to the line voltage, is never the phase voltage. What is the internal generated voltage EA of this machine at the rated condition? Okay, so now the keyword is rated condition. That means now IA is rated value. Okay, IA is not 0 now, and now I have to tell you the internal generated voltage EA at the rated conditions. So how I can find the IA for the rated conditions? So that means now I have attached a load. Okay, let's go back to the this whiteboard. Okay, now I have attached a load over here. It's my pen here. Okay, so now I have attached a load. It is now at the rated condition. And what is the, how much is the load drawing? What is the rating of the generator? So the rating of the generator I know is 50 MVA. And what other data I have? Okay, I'm looking at the data now. So it says that it is a 13.8 kilovolt, 50 MVA generator. So that means that to the load, it wants to supply 13.8 kilovolts line voltage. So it wants to supply 13.8 kilovolts line voltage. That means the phase voltage is the same value. And how I can now find IA? Because IA is now the key to finding EA, and now EA will be dissimilar from V5, so I can remove this because now there's some current, so the terminal voltage will differ from the armature induced voltage. I can also make some space by removing this. And I know the equation now. The equation is EA per phase is equal to IA per phase into RA plus JXS plus V phase for the load. And I know that for the load, the V phase is 13.8 kilovolts divided by the root 3. I divide the line value by root 3 to get to the phase value. And I know that the angle for this is equal to 0. And I know the value for RA and JXS. RA is 0.2 plus 2.5 J. These are the phase values. Okay, so you have to convert this all in the calculator by using the complex mode. And I want to find this gadget, but I am still not aware about this gadget. How much is the rated armature current per phase? So I know it is a 50 mega 50 MVA generator. So that means I know the formula for 3-phase machines. It is 3 V phase, I phase, cos theta, or I could use the alternate formula, which is under root 3 V line, I line, cos theta. And this is the apparent power. This is not the real power. So I multiply it with the power factor to get the real power. So now I can use maybe the above formula or the bottom formula. And we know that in the case of Y, IL and I phase are the same. So I may use the above formula or the below formula. IL and I5 would come to be the same. Let's take the above formula. So what is the phase voltage? It is 13.8 kilovolt divided by the under root 3. I'm using the top formula, and I phase I want to find, and cos theta I know it is equal to 0.9. It's 0.9 cancels with 0.9. Give me the value of I phase quickly. Quickly, I'm waiting on the chat window. Please give me the answer. Calculate this and give me the answer. I have some activity on the chat window. Maybe someone has given me the answer. The answer is 7.96 kilovolt. No, this is some previous result. Amir Noor 7.96 kilovolt. Amir, are you just copying Anam's answer? I'm asking for the current value. What are you telling me? Okay, quickly. Amir, do your own stuff. Don't copy from others. ठीक है, इसको जल्दी से कैलकुलेट करके बताएं आई फेस की क्या वैल्यू आती है. Shouldn't be taking that long. इसको करने में इतना टाइम लग रहा है. 50 मेगा को 3 से डिवाइड किया, अंडर रूट 3 से मल्टीप्लाई किया, 13.8 किलो से डिवाइड किया, 2.0963 किलो एम्पियर. ठीक है, किधर गया पेन मेरा? 2.0963 किलो एम्पियर. दिस आंसर सीम्स राइट. और इसका जो एंगल है वो क्या होगा? माइनस कॉस इनवर्स, क्योंकि लैगिंग है इसलिए माइनस कॉस इनवर्स 0.9. अब इसको इसके एंगल के साथ ये कैलकुलेट करके बताओ अनम जल्दी से. ईए पर फेस कितना आ रहा है आपके पास? ठीक है, ये आई फेस का जो आंसर है ये है 2.093 इंटू 10 पावर 3. ये तो इसका मैग्नीट्यूड आ गया, और इसका एंगल आपको पता है लैगिंग है तो माइनस साइन के साथ, और कॉस इनवर्स ऑफ पावर फैक्टर. ठीक है, तो ये इसका एंगल आप इसमें पुट करें. जल्दी से अनम बताओ इसका आंसर क्या आता है. ठीक है, ई ए पर फेस का आंसर क्या आता है? ठीक है ना, आपका आंसर सही है। मुझे दूसरा ईए पर फेस बताओ जल्दी से। ठीक है, ये एंगल -25.84 आता है, ये वेरीफाइड है। ठीक है, ये -cos−1 से एंगल लैगिंग में करंट का आएगा -25.84। ठीक है, तो यहाँ पे -25.84 आ जाएगा। और ईए पर फेस बताओ जल्दी से ना। ठीक है, इसमें सारा खेल सिर्फ अंडरस्टैंडिंग का है। इक्वेशन एक ही है, मामूली सी इक्वेशन है सिर्फ, लेकिन आपने डेल्टा वाई, लैगिंग, लीडिंग और इन सब का ख्याल रखना है कि सवाल में डेटा लाइन में है कि फेज में है। और आपने डायग्राम हमेशा पर फेज बनाते हैं, डायग्राम कभी भी लाइन में नहीं बनाते। और फेजर डायग्राम भी हमेशा फेज में बनाते हैं। अनम, नहीं निकाला आंसर आपने अभी तक? कोई भी किसी ने नहीं निकाला? इसमें क्या मसला है, सब कुछ तो वैल्यूज डली हुई है। इसको इससे जरब दें और ये ऐड करें, बताएं क्या आंसर आता है। Okay, sorry, I may want to switch back to English. Maybe Abdullah, he may be in the class. Okay, so you are going to put the value of I phase, which is coming from here, into this expression. And what is the final answer? Okay, and we are doing this problem, end of chapter problem number 4.2. Okay, so this is end of chapter problem, and the problem number is 4.2. Those who may have joined later, they can then look into the question later. No one has found the answer till now. That means I will have to find the answer for 2096.3 minus. Okay, we have a question answer from Anam Shafiq. The answer is Anam's answer looks okay to me. 11.542 kilovolt and angle is 23.9. Okay, so now you can see that EA has to be higher than the phase voltage. The phase voltage was 7.9 kilovolts, and EA has to be higher than that 7.9 kilovolt. It is 11.5 kilovolt, because it has to make up for the losses in here and in here. Okay, so this is a known case that for lagging loads, EA is normally higher than the terminal voltage. Now let's go to part number C. I believe this one was part number B. Let's go and check out the other parts. Okay, so we have done two parts, and now it says at the rated conditions we have found what is the phase voltage of this generator at the rated conditions. This we have already calculated. It was 7.9 kilovolts. Okay, because it is 13.8 kilovolts, and since the generator is Y connected, so we can find the phase voltage by dividing the line voltage by under root 3. So we have already done this part also. We have done A and B and C. Now we are at part number D. In part number D, it says how much field current is required to make the terminal voltage equal to 13.8 kilovolt when the generator is running at the rated conditions. Okay, so that means when the generator is running at the rated conditions, we know the value of EA is per phase is 11.5 kilovolts. Okay, we know that the value of EA is this. Now we want to find the uh, field current. Okay, and field current can be given from that graph, but that graph has not got the phase value of EA, it has got the line value of EA. So we can find the line value of EA by multiplying this by under root 3. So 11.5 kilovolt multiplied by under root 3 will give you the line value. What is this line value? Okay, so why we switch to the line value? Because the graph and the data in the question is always in terms of line. 11.5 kilovolt multiplied by the under root 3 is a value which is 19.9 volts, 19.9 kilovolts. Okay, so EA line is 19.9 kilovolts. So corresponding to 19.9 kilovolts, we look at the field current. So we are looking at almost this periphery of the graph. 19.9 is almost close to 20. So we have to supply it with a field current of about 10 amperes. Okay, is everyone clear about this? Yeah, because we take the line value, because the graph is always in the form of the line value, and it is a Y connected generator, so the line value is always under root 3 times the phase value. Okay, so now it says in part number E, part number D is also done. Is everyone clear about part number D? Suppose that this generator is running at the rated conditions, good enough, and then the load is removed from changing without changing the field current. So we know that if the generator is running at the rated conditions and suddenly the load is removed, then the terminal voltage becomes equal to the EA. Okay, if suddenly the load is removed, that means that IA, IA, RA and IA, J axis parts are gone to zero because IA goes to zero and EA and VT become same. Okay, if the load is removed, IA goes to zero, and in the same equation we can see that V terminal voltage would be equal to EA. Okay, and but this thing will influence this thing, not this thing influencing this thing. So VT will become equal to EA, and what is the value of EA at that point? EA at that point is equal to this 11.5 kilovolt, or it is 19.9 kilovolt per line. Okay, so this will become 19.9 kilovolt line voltage. Okay, so EA line or VT line both will become equal to 19.9 kilovolts because all of the EA would begin to appear as the terminal voltage. Okay, is everyone clear up till here? As soon as the load is removed, what happens is the IA part of that equation vanishes. Okay, as soon as the load is removed, this gadget vanishes because IA goes to zero and all of the EA will begin to appear on the terminal. So all at the rated condition, we have already found the line value of EA is 19.9 kilovolts. So your line voltage, terminal voltage line will also be equal to 19.9 kilovolt. Is there any questions? Kindly repeat this again. Okay, Asadullah wants this D part to be repeated again. So for him, if the generator is running at rated conditions, at the rated conditions, we have already found that EA is equal to 11.5 kilovolts per phase, or it is equal to 19.9 kilovolts per line. And suddenly the load is removed. Okay, so when suddenly the load is removed, what happens is this IA goes to zero. So in this equation, this whole gadget will go to zero and EA will become equal to V phase at no load. EA per phase will become equal to V phase at no load. Okay, and I've already calculated the rated value of EA, and all of that will begin to appear at the terminal if the load is suddenly removed. And I already know that EA per phase is equal to 11.5 kilovolts. So all of this will appear per phase over here, or if I'm talking about the line voltage, then this multiplied by under root 3 is 19.9 volts, and all of this will begin to appear at P phase. Asadullah, are you clear now? Asadullah, you are not clear about this. Are you clear about this now? Okay, so we can go forward to part number E, and as soon as this meeting ends, we will begin a new meeting after I save the recording. And in the part E, it says, no, we have already done part F. Okay, how much steady state power and torque must the generator capable to handle such rated conditions?